Here to talk about what we have done under the terms of the PEG award or sub-award. I should say that this is an example of a research project where once we get started, we started to have some different ideas. The work did not progress in exactly the same way as we imagined, but actually the outcome is very good, as I would like to show. What is our science objective? We'd like to study turbulent mixing, which is the mixing of various substances or maybe temperature in a turbulent fluid flow at high Schmidt number. What is the Schmidt number? That's the ratio of kinematic viscosity of the fluid to the molecular diffusivity of the diffusing substance. So a very high Schmidt number occurs when molecular diffusivity is very small. One example is salt in the ocean or liquids in general. And what happens when the molecular diffusivity is small? Then we can have large gradients that build up locally. It means that we will be somewhat difficult to try to resolve what happens. We will have to have a very small grid spacing, and that's what we're trying to do here. For the scalar field, we like to have a scalar field up to 8192 cube, but the velocity field doesn't have to be. So we can save a lot of computer time compared to trying to simulate 8192 cube or both velocity as well as the scalar field. And what is our starting point? Our starting point here refers to somewhere around March 2016, which was after we were able to use funds from the PEG sub-program, sub-award, to support a visit from our Japanese collaborator, Toshi Goto. He has the idea of using different numerical schemes and different numerical resolutions for the velocity and the scalar. What we try to do is to try to put together everything first using pure MPI, and we have two separate communicators. So we have some different nodes. Most of the nodes of the program will be running the scalar field. Some of them will be running the velocity field. And so we wanted to work with the IMT team, but as I said, we actually proceeded along a somewhat different path. I wanted to show that we are able to achieve overlap between communication and communication in a very significant way that is specific to the use of the combined compare-finite difference schemes. I think many of you will be familiar with what compare-finite difference schemes are. What we mean by combined here is that we actually will be calculating the first derivative and the second derivative at the same time, and we do that, and we have to do that. We have to do that in three spatial directions. But is it possible to overlap communication, let's say, for direction number 2 and computation for direction number 1? We also found that we can get the best performance by using some relatively advanced features of OpenMP. In particular, we have one thread. We start with two threads. One thread will handle communication. The other thread will handle computation. And then that other thread is actually going to spawn off another set of threads. That's why we referred it to nested parallelism, and we found that we were able to get about 35% faster, and the improvement was more significant at larger problem sizes. And I hope I will also have time to talk a little bit about my student Matthew K. is here. He's going to graduate soon, by the way. And he worked with, also informally with the HDFS group, and we found that we can we are able to achieve some data compression for the data that we have to store. So on the screen now, two schematics. They're actually the same solution domain, but one of them is divided more coarsely, and as you can see, for the velocity field, and the other is divided more finely with a smaller grid spacing that is implied. And the physics of the problem is that the scalar field depends on the velocity, but not otherwise, not the other way. So what we have to do is to send information from the velocity field to the scalar field. And there's a little bit of non-trivial challenges here. You might observe that the velocity field, this subdomain is divided along what we will call x2 and x3 direction, but not in x1. In contrast, the scalar field is under a three-dimensional domain decomposition. And why do we do that? Actually, to be honest, we borrow the practices of some of the some researchers in Japan. But the advantage is that for a three-dimensional domain decomposition, there is no transpose. There is no transpose. There's no transpose involved, and as opposed to, let's say, three-dimensional FFTs. And there is a method, there is an algorithm, that would allow us to, nevertheless, to compute what we need for the scalar field as long as the velocity field sends the information over without information in core or at once. Now, this transfer, of course, we want to make this communication relatively efficient. And so we have a pencil for the velocity field. We have a pencil. It's like I think with this illustration we have a 2x2 communication. So this pencil is actually subdivided or carved up into several smaller ones. And then when we use MPI derived data types to try to simplify the programming, and we have it all sent to one of the one particular MPI task was responsible. One of the MPI tasks. And then this MPI task is going to scatter information among its neighbors along the direction that we refer to as the IO communicator, which is along the X1 direction. So we have written up a paper submitted to Computer Physics and Communications. We received quite favorable reviews a couple of weeks ago. Hopefully we'll be able to get it published sometime over the summer. And there are some more details in there. If anyone is interested, we can send the revised paper. We're going to working on the revised paper now. And so, what about the performance? And what is our basis? Our basis is if we were having blocking communication, which of course prevents any kind of overlap. And also, if we use pure MPI without using the benefits of OpenMP, what do we get? Number of processing elements here. This is what we call B for blocking and S for single threaded. This is the number of this is the number of cores. All of these data are for the largest problem size, 8192 cube for velocity field, and for the velocity field, I think it's 1024 cube. And when we are measuring weak scaling percentages relative to a 1024 cube problem. But for strong scaling, so we refer, starting with 64K cores, we double the number of cores, then we get 85%, and then another doubling, we get 80. One might argue that this kind of scalability is sort of respectable, but we wanted to do better. And so we tried some strategies for overlapping between communication and computation, which is overlap. We keep it single-threaded, and we can see that the performance improves. Let's say 256K is actually the number of cores that we're going to use for production purposes. So the timing goes down from 10.8 to 9.5 seconds. We also tried multi-threaded OpenMP, which I'm going to refer to as basic OpenMP for the time being. And then we went down from 10.8 seconds to 9.9 seconds. Some improvements, not as much. We tried both of these tricks, overlap and basic OpenMP, and we were down to 9.3. But we actually found that if we're going to dedicate one of the threads to communication and the other to computation using nested OpenMP, which is what we can do with OpenMP version 2 point something, And then we actually going down from 10.8 seconds to 8.1 in 1 second. So the Schwann scaling for quadrupling 4 times increase in the number of cores, 64K to 256K, we have 94%. So I would think that this is about the best that we can ever hope for, or actually this is better than what we imagined that we would achieve from the beginning of the project. And the last, okay. I'm going to talk about Open HDF5 very briefly here. We're grateful for the interest of the HDF5 group. I think Gert Heberg had regular Skype or similar forms of contact with my student every 2 or 3 weeks or so. And so, of course, we use open the HDF5 modules made available by the HDF5 group. We also try some new features, in particular product compression. Every snapshot that we save is 4 terabytes. Although we are very fortunate to have a 2 petabyte quota on DN9, nevertheless, it would be nice if we can make our file smaller. And we are using the feature of virtual data sets so that we have I think we have a very high degree of flexibility. Let's say if we save our checkpoint with running the code on a certain domain decomposition layout, we can read it back in without problems, even if with a different number of cores and so forth. We also try to reduce the number of small repeated reads, which will be not very efficient. We'll have one MPI task with the information that says that, well, which file contains what. And we use Dartian and MPI timers to measure the IO performance. And here's a very short description of it. The original scheme took, let's say, 30 seconds to read the data. And the diagnostics show us that there are reads of essentially different sizes. There are some 200,000 read operations where we have 100 bytes or less. But with an optimized scheme, you can see that we have a tremendous improvement over a factor of 12 in the timing. So to the last slide here, definitely the big award make our work on high-speed number mixing possible. We have a dual communicator parallel program, dedicated OpenMP threads for communication. We are able to achieve something like 90% rescaling over substantial geometry problem size. And we'd like to thank the NCSA staff for their very dedicated and excellent assistance. Performance monitoring, they answer our deep questions almost at any hour of the day, I would say. And I would certainly agree with the assessment that as our community moves towards a new architecture, this morning we heard about nice landing, and of course there's GPUs. I think this is very important that the science teams receive good support for code development.